You can do it carefully, but suppose we have a system of point masses distributed along a line. We want to discuss its behavior as there get to be a lot of the point masses, enough that we can sort of chunk it up into small volumes and treat this as a continuum. Let's call this length delta L, and we can define a mass per unit length at each x. So, think of x as the position of this coarse graining of the near continuum of point particles. So lambda of x is going to be the sum of over all I in delta L of the masses. We've got M1, M2, M3, and so on, divided by that length delta L. And then, given this density, we can define the kinetic energy. Where are we missing? Oh,
Josh.
Josh and John. Oh, okay. Josh and John. Okay.
John will be here though.
Yeah. Okay. Good. Yeah. Yeah. Like, are all the J's staying at home? I should go. The kinetic energy, and now this is the contribution of the kinetic energy of just this block of particles. It's going to be a half times the density times the delta L will be the mass times x dot squared, where x is this average position of that. Then, if we want to, let's see, what I want to do is to replace x with a field. So let's suppose that the equilibrium position is characterized by some x naught, and that's the equilibrium of these masses here that will, let us suppose, tend to move roughly together. We're in some very slowly changing potential, perhaps. And so if I let phi be a measure of the displacement of delta L from its equilibrium position, then phi dot is going to be x dot, and I can write the kinetic energy in terms of that displacement phi, delta L and phi dot squared. And what I want to do here is let phi go to a continuous variable. So think of phi as the displacement of this bunch of particles, a very small displacement away from its equilibrium. Then, if we have a slowly changing potential that depends only on this displacement from equilibrium, then the potential, of course, we can write in a Taylor series dv dx at x naught x plus 1/2 squared v dx squared times the displacement, and higher order terms that we can neglect. But since x naught is the equilibrium position, we can take the zero of the potential to be zero, and at evaluating the gradient of the potential at the equilibrium position also gives us zero. So the first term is really the quadratic one here. Now, what I want to do, and this is well, this is one way to go about this. I'm going to multiply by delta L here, and then we have the second derivative of V with respect to x at x naught, delta L squared, and then I'm going to divide x minus x naught over delta L, quantity squared. So this is just some constant. But what I can do is, in the limit as delta L becomes small, x minus x naught, the displacement over delta L is just going to be the derivative of this displacement phi, how that's changing with position. And that lets me write the potential as, now let's see, I've used two delta L's here. Then I'm going to define, here, let me make a definition here. Let's let, what do I want? Delta L times d squared v dx squared at x naught. Let's call that sigma, some constant sigma. Then the potential is 1/2 sigma d phi dx squared times dl. And that is, excuse me, that puts it in terms of basically a gradient of this displacement. So now I can write the contribution to the Lagrangian, let's call it delta L, as the contribution to T minus the contribution V. You know, this is really just from one of these segments, and so we have to sum over all the segments. So this is going to be, or where did I put the kinetic? It's half lambda delta L phi dot squared minus 1/2 sigma, let's call this dl d phi dx squared. And now the total L, I can integrate this over all displacements, or in the continuum limit, I'm just integrating over all x. What I have is 1/2 lambda phi dot squared minus phi prime squared times, whoops, sigma, like this. And suddenly we're doing something that looks like a field theory. Now, if we have a fairly uniform material, we can take this lambda and this sigma to be constant. I mean, we're doing some very radical approximations here, but just imagine these displacements to be infinitesimally small, and you can see that we can arrive at something like this. Now, if I rescale this, and let's see, how do I want to do this? Let's write the action is the integral of L dt, which is now, okay, so notice what happens here. We have an overall half, and I'm going to pull out sigma, and I'm going to define 1 over v squared, defined to be lambda over sigma. So now what we have is 1 over v squared phi dot squared minus phi prime. So I'll write it out. d phi dx squared. Integrated over both dt and dx. Now, if we vary that, this is a class that's good at varying actions, right? I just showed them in classical how to vary an action. So You're expert. Okay, so I want to set the variation of the action to 0. And this goes very much like I would vary particle position, only, phi is really a function of x and t. Now, that's a field on this one-dimensional, well, let's say two-dimensional space-time. Okay, and when we vary this, right, full integrals here, then I'm going to get 1 over v squared times 2 times phi dot del phi dot minus twice, let me just call it phi prime del phi prime. And because we're integrating over both x and t, I can integrate both of these by parts. So we have sigma over 2. The 2 cancels. We just have this constant sigma. And then we'll get surface terms. Okay, if I write this as ddt of 1 over v squared phi dot del phi. So when the ddt hits del phi, I get the term we have. But there's another term when it hits the phi dot, so I have to subtract that off to have the same thing here. So I replace this by that, times the 2's cancel.
And the v is a constant.
V is a constant, yeah. Yeah. And it's units or velocity. It connects the ddx and the ddt terms here. So then I integrate this to the endpoints of my integration where the variation is taken to vanish. So this term integrates to the endpoints of the motion, and since the variation del phi is 0 there, this term is going to be 0, and we just end up with minus 1 over v squared phi double dot del phi. We do a similar thing for the potential. For the spatial derivative. I can write this as minus d dx of phi prime del phi, where I have to add back in phi double prime del phi. And again, the total spatial derivative integrates to the surface, where again, at the spatial boundary, we require the variation to vanish. We're holding the ends of this system. So the ddx term is going to vanish, and we're left with phi double prime del phi, and we're still integrating dx dt. Now, this is equal to 0. I can cancel that overall constant. But now we have 0 is some arbitrary variation of phi times a constant phi double dot plus phi double prime dx dt. And the usual argument applies here when we vary an action. Suppose the term in brackets is non-zero at some point. At some point in some time, x and t. Pick some x and t and suppose it's 0. Then I can let del phi vanish everywhere except at that point and have just a little positive blip, which means evaluating this integral is just basically the xt area of the blip times that value of delta phi times the thing in brackets, which we said was non-zero. But that can't be 0, so my assumption was wrong, and the term in brackets has to be 0 at that point. Now, that point was arbitrary, so I can do that same argument at every point, and that shows me that 1 over v squared minus 1 over v squared d squared phi dt squared plus d squared phi dx squared is 0, and that is a one-dimensional wave equation for a scalar field phi. So we've gone a bit coarsely, I admit. And you can do this very carefully. You can do this in 3 dimensions and get this out rigorously. The conditions that lead you to a wave equation like this really involve very small displacements, and you really can ignore the change of the density and so forth over that infinitesimal region and get this out with very radical constraints for what's changing. Okay, so this is the simplest wave equation you can imagine writing. This wave equation, you can derive this from Newtonian mechanics for the displacement of a string. So if I fix a string between a couple walls, and I send some wave along that string and measure the displacement from horizontal as some variable u, you can go through a nice classical mechanics problem where you look at the tension in that string and the mass of the little segment of string and rigorously write Newton's second law for a bit of the string. You get just this sort of differential equation for the propagation of a wave along the string for small displacements u. So we can get continuous wave-like equations, for example, continuous equations out of a discrete set of particles by taking this kind of a limit. There are other ways that we can generalize this that are interesting. As I said, if you do this problem in 3 dimensions to this level of approximation, that d dx becomes a gradient. So if d phi dx, our one-dimensional problem, goes to 3 dimensions, then this becomes a gradient, and our action is now 1/2 dt, and then we have the integral over adding up infinitesimal volumes, and then we have, I'll change the constant, let sigma be -1, so we have d phi dt squared minus grad phi grad phi, and then here we have some velocity. This v turns out to be the velocity of a wave on the string, or the velocity of propagation of small excitations of our field phi. In fact, if we let v go to c, this becomes something relativistic looking, because notice we've exchanged just a time integral. We've actually got an integral d4x here over all of space-time, or any region of space-time, and then we could have 1 over the speed of light, phi dot squared minus grad phi dot grad phi. I'm going to have you vary this. I'm going to generalize this a little bit more and have you vary it for an exercise. But this is the action for a massless Klein-Gordon field. Scalar field. Right, so the Klein-Gordon equation describes a scalar field. Usually it has a mass, and I'll show you how to add a mass to this. But let me see what else I wanted to say about this. There are some general features here. Notice what has happened to... No, let me give you your exercise first. To make it massive, mass of the Klein-Gordon. The kind of term that we add here, and I'll call this the Klein-Gordon action, is a half the integral d4x. So d3x over all space and dt is the fourth dimension here. Then we have 1 over c squared. These really should be partial derivatives if we're, and they should have been partial derivatives over here, in fact, because phi is a function of two variables, x and t. So really, these primes and dots should be d phi dt and d phi dx, partial derivatives. Same here when we have four variables. So this grad phi dot grad phi, and the term we add to get mass is mass squared times phi squared. So that term will give the Klein-Gordon equation, and we define, we're going to see this often enough. This comes up in E&M. You remember your E&M, the wave operator. Box is going to be, oh, now I have to do this backwards. I'm sorry. Usually I define this with a minus sign from here, but the Laplacian plus the time derivative, right? Usually I would write minus this plus that. I'm going to put the minus sign here because in field theory, choosing a metric with time plus 1 and minus 1 on the space makes some of the equations work out more cleanly. There are enough conventions in quantum field theory that it's hard to change one without having to change a half dozen. So I'm gonna define, usually in special relativity, general relativity, we have minus 1 plus 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 for the metric, and we're going to talk about relativity in a few minutes. But here we take the opposite convention. It's still invariant, it's just minus the invariant we had. This operator is called the D'Alembert. It's a four-dimensional wave operator. And your exercise is to just vary it. Show that del Klein-Gordon action equals 0 gives the Klein-Gordon equation, which is usually written as box phi is m squared phi. Now, that's the simple form. There are actually some units here. If you want to get the right units, we need m squared c squared over Planck's constant squared. Remember, Planck's constant is momentum times position. mc is a momentum, so mc over h bar is 1 over a length. So the units here are inverse length. Phi has units of inverse length too. So in fact, this goes 1 over length of the fourth. So this action with length of the fourth here is scaling back. All right. If I put the units in, I'm going to have m squared c squared over h bar squared times phi. And this is the Klein-Gordon equation. I believe you guys worked with it a bit in Charlie's class. Did you work with this some?
I've been reading through the book a little bit on classical field theory,
Mhm.
so I've
No, I don't. I'm like I might be
outside of that.
rusty, but no. No, we just
You just did E&M.
we just
Okay.
solve Maxwell's equations.
All right.
Get
Okay. This is simpler, right? I mean, Maxwell's equations, if you choose the gauge right, give you 4 copies of this equation,
I see.
right? With 0 mass. And instead, you'd have a source over here. You can have a source for the Klein-Gordon equation too, so far as that goes. If you wanted to do the Klein-Gordon equation with a source, you would add an additional term to the action that would give you basically box minus m acting on phi is some source j. And that's exactly what you solve over and over for Maxwell's equations. This applies to all four components of the vector potential, or to the electric field or the magnetic field. They all satisfy this sort of wave equation where these are the usual electromagnetic sources. So it's not like you haven't seen the equation before or have some idea how to solve it.
Yeah. M squared.
No, is it? Let's see. Yeah, I'm sorry. M squared. Yes. Did I get that right here? Yeah, it's m squared. Yeah, which is, it's sort of a funny way for math to come in. This is this equation with 0 here is in fact where Schrodinger started, right? Schrodinger would have written this equation because it's a natural relativistic equation for a particle wave. If you want something for a plane particle wave, what you really want is something like I over h bar p dot x minus energy times time, right? A relativistic plane wave. And if I apply box to this, then right, a is just some constant. That's going to be minus 1 over c squared d squared dt squared plus L squared, acting on e to the I over h bar p dot x minus dt. All right, this includes the Planck relation. E over h bar is a frequency, and the de Broglie relation, p over h bar is a wave number. Right, so the de Broglie and Planck relations are sort of built into this idea. So we know that a wave has a wavelength and a frequency given by these expressions as of 1917 or so. And so you can write a plane wave, k dot x minus omega t, in terms of energy and momentum. Right? And this is a way to put particle properties into a wave-like thing. Well, let's carry out these derivatives. We have minus 1 over c squared. ddt is going to pull down minus I over h bar times e. It's going to hit this, and it's going to pull down that squared, and then leave the exponential. Del squared is going to pull down the coefficient of the x. So we're going to have plus I p vector over h bar quantity squared. All of this times the wave again. All right, and now if I pull out, let's see, let's fix the signs here. That sign goes away. I squared is minus 1, so this term becomes plus. So we have e over h bar c. Then here we get minus p squared over h bar squared. H bar squared, c squared. There we go. That's e squared. Everything's squared. Times the exponential, e to the I over h bar. I'm going to write it as p mu x mu, four-dimensional dot product. But what I mean by that is this. Minus that. Now, look at this. If I pull out the h bar squared c squared, then we have e squared minus p squared c squared. And for now, that's just shorthand. There's a question.
Just discomfort about the sign, but I think it's right. It's on the e squared, on the e squared term.
Yeah, okay. That sign goes away.
Yeah, because of
I squared is minus 1.
Yeah.
Cancels that.
Yep, I just had to think of that negative as like.
Yeah, sure, yeah.
For instance,
that's
negative 1.
Yeah.
Yeah.
It's, Okay, what is this? What's e squared minus p squared c squared?
M squared.
That's m squared. Yeah, so this is m squared over h bar squared c squared here times our original psi. So if you try to build a plane wave, four-dimensional relativistic plane wave, where you use the de Broglie and Planck relationships to replace the frequency and wavelength by energy and momentum, then that plane wave satisfies the Klein-Gordon equation. And I think Schrodinger would have done this. The problem with this in Schrodinger's thinking would have been that this operator contains second time derivatives. And that means you need two initial conditions, essentially initial position and initial momentum, which, due to the uncertainty principle, you do not have in quantum mechanics. And so Schrodinger wanted a first order equation. So we might as well go ahead and do this. Not what I planned. Have you guys seen this? Do you want to see this?
Yeah.
So let's turn that into the Schrodinger equation. Now, let's see. Yeah, it's just a matter of where we want to do the approximations. Yeah, let me do another quantum step before I get the Schrodinger from this. If I want to extract the energy of this wave with an operator, what do? Right? I can take a time derivative.
DDT.
So if I take minus I h bar ddt on psi, that's e psi. Right? Let's see. Oh, plus. If I take minus I h bar grad psi, I pull out p. So we can say that this plane wave function is an eigenstate of these operators with the eigenvalues of energy and momentum. And so we can actually identify an energy operator, I h bar ddt, and a momentum operator, minus I h bar grad. And that is useful for getting the Schrodinger equation, because I can come from this form. I can come from the energy relation, E squared minus P squared C squared equals M squared. I can solve for the energy. So I can look for the positive energy solution. This is going to be M squared C to the fourth, actually.
Right.
Yeah, okay. So this becomes P squared C squared plus M squared C to the fourth. And now if I make it non-relativistic, I can pull out an MC squared and write 1 plus P squared over M squared C squared. One of the C's cancels. And now, non-relativistic approximation, I can write that as MC 1 plus P squared over 2M squared C squared. And that's just a constant M squared C squared, MC squared. Right? Plus, and now one of the M's cancels, I have P squared. It's just the 2M, it's just the usual kinetic energy, classical kinetic energy. So now, and if I wanted, I could add a potential energy to this, right? Let's just carry along whatever potential I might want here. So now I can write energy equals mc squared. That's nice. Plus P squared over 2M plus some potential. And now I make these operator replacements. I h bar d dt is mc squared plus 1 over 2m. The p squared becomes minus h bar squared, del squared, and then I have the v. And now I let this act on a wave function. Let's call that wave function chi for the moment.
Okay.
mc squared chi. Question?
Yeah. We get. And the dot is the time derivative.
Yeah.
Yeah.
I meant to write the chi dt here. H bar squared over 2m del squared chi plus v chi. And finally, I'm going to let psi equal e to the, let's see, what do I need? I need mc squared over h bar and minus I mc squared over h bar times t should do it. Because now the time derivative pulls down this coefficient and gives me an mc squared here. And then just comes along for the ride in every other term. So what I have is I h bar, chi is this times psi. All right, where this still depends on x and t. So what I get here, I h bar e to the minus I mc squared over h bar t times d psi dt plus mc squared e to the minus I mc squared t over h bar psi equals m squared c squared. All right, I'm just going to write chi here. In fact, okay, these three chi's, I can pull out that exponential factor, e to the minus I mc, because it only depends on time. So I'm just going to get mc squared psi minus h bar squared over 2m del squared psi plus v psi each times that factor. Well, now that factor cancels everywhere. The mc squared cancels between the two sides, and I'm left with I h bar d psi dt is minus h bar squared over 2m del squared psi plus v psi, the Schrodinger equation.
Is that worth a Nobel Prize?
You all right?
Sure. We'll go.
Can I ask a question?
Yes, of course.
We lost covariance, though, didn't we?
Oh yeah, oh absolutely.
So
Yeah, it's still three-dimensionally.
right, but it went from a covariant expression
Right.
and ended up.
This is a non-relativistic approximation.
So it was that square root
Klein-Gordon.
expansion that led
Oh,
to
yeah.
that.
Yeah, we dropped higher order terms here. Right? We just kept the lowest order. Actually, if you want relativistic corrections to the hydrogen atom, just keep the next term in that expansion. And that'll give you, I forget what the correction's called, but it's the relativistic first order correction to Schrodinger. And, test out right.
Yeah. But that was the problem. It's not covariant.
Right.
That's where
Yes.
Dirac came in.
And this is what led Dirac to be Dirac. And we will go through a lot with Dirac. That's
I had a quick question.
the principal new field theory that you guys probably haven't seen. Yes.
So on the left side, you have a KG equation is m squared c squared over h bar squared. But over there, you have c squared on the bottom.
Oh well, that's probably wrong. Let's see. What do they do?
Oh, I think maybe you just made that as m squared instead of m squared c to the fourth. I think if you make e squared minus.
Oh, that should be c to the fourth here. Like
and
that.
So yeah, okay,
Yeah.
that cancels out.
Yeah, this should be mc squared. Mc squared squared.
Yes.
So yeah, that's right. Good. Any other unit corrections here? But yeah, we basically got this. So it was actually this field theory, which we got from like looking at continuum limit of some particles that really ultimately led to the Schrodinger equation.
If you kept all the higher order terms,
Yeah.
it would become covariant.
It would become hideous
But it would,
because
yeah.
you're doing an expansion in p squared. That's the Derivation. So it would have all orders of differentiation. It would be a horribly infinite order differential
But
equation.
you would approach covariance.
But yes, yeah, sure, you should. Yeah, it's probably not the easy way to do it.
Prove.
But yeah, that's right. Yes.
And so, yeah, one other question I had was that the equation on the top, what is J?
Oh, here.
Yeah.
Oh, just a source.
Oh, okay.
You can add, just like E and M. If that was the vector potential, this would be J mu.
Right, okay, got it.
Davis, did you have a question?
No, I was gonna say that the way to put back covariance
Yeah.
would be to redefine the derivatives there. So
Which derivatives? How would you
So-
say it? No, let's do it. We'll get you.
He's
a
talking
Nobel
about
Prize.
covariant derivatives.
hang on.
You can race to the bar for this.
Oh no, I'm
Don't mind the camera. Say what you have to say. Don't worry.
No, let's try it. What is it?
Okay, I was thinking. Okay, so special derivative there.
The
No,
gradient.
yeah, over here in the when you already have the Schrodinger equation.
Yeah.
How to put
Del squared.
yeah.
Yeah.
So the del squared you define it covariant derivative.
Yeah. So the full expansion would give powers of del squared, but what Dirac actually did is say, no, that's got to be linear like this one.
Right.
Yeah, that's what he did.
So he's saying, what if we put the derivative there as a covariant derivative?
A covariant derivative. All right. Covariant with respect to what?
Yeah, that's
Right.
that's
I mean,
hence the hesitation.
I mean,
I realize.
well, I mean,
realize-
you could put some sort of four-dimensional covariant derivative there. But,
Yeah, like-
that's the Derivation.
I was thinking
Right.
of something
I mean, just
like that.
d mu. That is the Derivation. Right?
Yeah,
Yeah.
but
Now, another thing to notice,
that doesn't seem to do it.
these operators are relativistic. Take a look at this. If I, all right, the four momentum is,
Professor Wheeler, could you repeat the statement you just made?
uh-huh.
Those operators
These are relativistic.
Okay.
Form a relativistic vector.
Yeah.
Okay. So the four momentum is really E over C. And if I lower the index, then we have E over C, and we have this becomes minus P, the way we're doing it. So if I write I H bar P alpha is I H bar ddx alpha, because this is covariant, not contravariant, so I need this down. And identify that with E over C and minus P. What I have is P, the three vector part is the three vector part of this, I H bar rad, and E over C is I H bar ddx0 is 1 over C ddt. And the C goes out, and we recover these operator identifications. So actually, this identification is nicely relativistic.
Sweet.
Okay, so I want to look at one thing that has changed. Let's start back. Okay, so that's your exercise. Vary the Klein-Gordon action to get the Klein-Gordon equation. Let's look at this.
Yeah, no, this is
Right. This is the integral of L dt, which means that L itself has to be, all the rest of this has to be the integral d3x of 1 over c squared, and then everything here. Which is all fine, that's all well defined, except what kind of an object is L now? In classical mechanics, we're used to L being t minus v,
Yeah.
and it's then a function of coordinates and velocities, maybe time if you like.
Sure.
What do we got here? What's this kind of object called?
Lagrangian density.
Yes. Well, this is a Lagrangian density.
Yeah.
Call that curly L. That is a Lagrange density.
Because of the camera, like 20 minutes from now, people will be like,
Yes. Excellent, David. Okay, so this L is now a functional of phi dot grad phi. That's a functional, not a function. Which means, so does everybody know what a functional is? Right, a function is a mapping from reals to the reals.
Mhm.
You give me a number, I give you a number. A functional mapped from a function space to the reals. You give me a function, I give you a number. All right, an action is always a functional because this is if L is a function of coordinates and velocities, but you're integrating over that to find some number s, you have to give me the whole path of motion, the whole curve, in order for me to compute the action. So this action is actually a functional of the path. You give me a function, I give you a number. It's not a whole lot more complicated than functions, but it is a different object. And we're going to be at least notationally correct here. And when we vary this, what we're really asking for is the vanishing of the first functional derivative. Not the vanishing derivative of a function, but the vanishing first derivative of a functional. We're doing the same thing. We're finding an extremum. So you've encountered functionals before, but maybe not named them. They come up now and then. The work. Okay, work is the integral of f dot dx. So if I calculate f dot dx, integrate that along some curve, that is the work done in, by that force along that curve. But notice that this could depend on which curve I take. So you give me a curve and the force, I can evaluate the work along that. But for a non-conservative force, that work is going to be different for different curves. So work, in fact, is a functional. If a potential exists, it's minus the integral of f dot dx. A potential exists exactly when this integral is independent of curve. And now, this is a function, this is a functional.
So it means if the force is non-conservative, it won't have a potential.
Exactly. You can still compute the work, but you have to specify a path.
But W depends on two things, the function and the curve.
Yeah, the force. Yeah, you got to know the force, but the force is different for different curves, and so you have to know the path of integration too. So you have to know the force, you have to know the curve. But for a given force, work is a functional. For a given force field, say.
It depends on two quantities.
Yeah, it does depend on both. That's, yes, for sure.
And that's still a function.
Let's see, it's, well, let's see. For a given problem. So, given the force on a particle at every point, knowing what that is, put that particular function here, and then the work done by that force along any path is now a functional of that path. So fix the force, and you have a functional of curves.
So this is a functional of the path.
Yes. Yeah, you change C, you change the work.
Right.
Yeah, think of the dissipative force, right? Of course, that's, different. Yeah, it's fill the room with water, walk to the door that way or walk to the door that way. I did more work going around that way. Blow. Okay. Now, we have the Lagrange density. So it's all of that. Here's the Lagrange density. So now we can write the Lagrangian as the integral over 3 space of the Lagrange density, and then the action is the integral of L dt. This means that our definitions, we don't really change things in working with fields instead of particles. But we do need to, this is my old one. We do need to be a little careful. So, for example, if we want the conjugate momentum, right, we know that if we have a Lagrangian that depends on x and x dot, that the conjugate momentum p is the partial of that Lagrangian with respect to the coordinates, the velocities,
Yeah.
with respect to the velocities. So we're not really going to change that. In field theory, what we have is, the Lagrangian, it depends on phi and phi dot and grad phi. And we do want something like the partial of the Lagrangian with respect to phi dot, only the Lagrangian is a functional. So the Lagrange density is a function, but the Lagrangian itself is a functional. So what we need is what's called a functional derivative of the Lagrangian to get the conjugate momentum. All right. Now, it's a lot like an ordinary derivative, and especially with the regular quadratic field theories that we use, we'll be using throughout this semester. So it'll be a whole lot like taking a derivative, but what happens here is, we need the functional derivative with respect to phi dot of this functional d3x L, and now I'm integrating over x. I take the functional derivative with respect to some x, let me call it y even. Right? So the functional derivative with respect to phi dot at y of the Lagrangian density integrated over x. And now I can interchange the order here and write d3x of the functional derivative of the Lagrange density with respect to phi dot of y. And then we're going to get cute with the chain rule. And we're going to say, all right, so pi is integral d3x of, and this is going to be pi of y, in fact, of, all right, let's see, do I want to do an explicit example here? I can take the partial of the Lagrange density with respect to phi of x times the functional derivative of x with respect to y. Anybody care to guess what that is? This is phi dot. So, for example, if L is a half phi dot squared plus stuff depending on x, then this term is easy. That's just partial with respect to phi dot is, I'm going to get 2, so I'm just going to get phi dot of x. So that's fine. But the change of the one set of parameters with respect to the other is a direct delta function. So the partial of xi with respect to yj is going to be delta ij. Let's be differentiating the same thing, but then del 3 of x minus y. And let's see. Did I do my chain rule right? I haven't really done, let's see. Now, I'm a little worried about how I've written this expression. I'll come back to that. What happens here is I get a delta function here. If I have, let's see. I'll give you a correction on that. Let's just do one variable here. This gives me a delta in x minus y, which I can then integrate to get, in this case, it'll just be the integral phi dot of x times the delta x minus y dx is going to give me phi dot of y. So I come out with the conjugate momentum being simply phi dot evaluated at y now. So we get a delta function in there. I'm fretting about the way I've applied the chain rule here. But let me come back to that after I have a look at it. But what's going to happen as we proceed is that we're going to find ourselves dealing with densities on occasion. We may have a momentum density. So the momentum might be written as the integral of a momentum density over some parameter like this. These sorts of things come up in field theory, and we'll work carefully with how to work with these. Now, let's see. Yeah, let me work through an example here. Suppose our Lagrange density is massless Klein-Gordon So we have phi dot squared minus a half grad phi dot grad.
Professor, can you just give me a minute to change my battery?
Sure.
Please. Thank you.
There is a method. We have the Minkowski method. Right. This is a half d mu phi
Yeah.
d nu phi a to mu nu. So yeah, we have a metric here.
Yeah. That's another half.
Now let's see. So it would be hard to write a relativistic action without the Minkowski metric.
So with your signatures plus minus minus minus.
Yeah.
Okay. So okay.
Yeah, it's just an overall sign that probably cancels, right? It's hard to find an expression where that sign matters. But a few crop up in field theory. Let's see, I want to do this again because what's in my notes here is slightly different than what I've just said. So let me say it the other way, and one of these will emerge as right. Let's go back to our statement that the momentum is the partial of the Lagrangian with respect to the velocity, the time derivative of your field in this case. And now, if I replace that Lagrangian with a half phi dot squared minus grad phi d3x, then the functional variation here, all right, this is a functional, so I should write this. But I'm still going to get what you think. I'm going to get 2 times the half times phi dot del phi over del phi, and nothing here, d3x. So it's just the time derivative of the field, but integrated. Now, we can identify this as a momentum density. Which we integrate over space to get the momentum. And now, when we start to quantize this, so we can write integral of pi d3x as the momentum. So what we want is for there to be a commutation relation between now operators. The conjugate momentum satisfies a fundamental Poisson bracket with the field. That's going to become a commutator as these become operators, and this is going to be IH bar. But when we put in the density here, we have now the integral d3x of pi, which becomes an operator with phi, which is an operator. And that needs to be IH bar. So what we can do here is that this commutator of, say, pi hat of x with phi hat of y, that needs to be a delta function. Del 3 of x minus y. And then we still have the IH bar. So what we'll find in field theory is that the momentum density with the field is IH bar times a delta function. So you get nothing if these are at different positions, but you get quite a spike if they are at the same position.
A Dirac delta.
Dirac delta. Yeah. Is everybody familiar with Dirac delta?
Yeah.
Yeah, cool distributions. All right, this should be minus. No, sorry. Okay, so we'll do this in more detail eventually. Now let's see. We started at 3:30. Okay. Let me know if anyone hears cows. All right, special relativity. What needs to be said about special relativity?
It's special and it's relativistic.
Okay. So done now. Okay, so
You have to start out with some invariant quantity, so line element or whatever, ds squared.
Yeah, so here, I'll draw you a picture of a two-dimensional space-time on this board.
Two-dimensional space-time. There it is.
There it is.
Yeah.
Done.
Yep.
Good. Okay, so now,
Right, yeah.
but there are some things we agree on, right?
Wait, would that be a 3D space-time because you have time?
No, 2D space-time. Because time is one of the directions here.
Oh,
Wait,
So,
okay.
yeah.
Professor Wheeler, I'm not seeing any time direction there on that.
Well, we got to work on that, right? So-
Yeah.
But sort of loosely, I want time up, and I want space going kind of like this. But we need to be a little bit concrete about this. We need to say, well, how do we measure this stuff? So we start with something we agree on.
Yeah.
If time proceeds generally upward and space generally laterally, and we all agree on what? Fundamental postulate of special relativity, speed of light.
Yeah.
The speed of light we all know is 1.
Sure.
All right. So let's draw a slope of 1 or -1. That would be fine too. And those are the directions that light goes. So since we all agree on light, let us always say that light travels at 45 degrees when we draw our space-time. That much we can agree with. Now, how are we going to set up coordinates in this thing? So we've got light going off at 45 degrees. And now, Davis is flying along in his rocket. Davis is moving off at some constant velocity. You feel no forces.
Okay.
Right? You're moving straight line, constant speed. And I've drawn that so that you're covering less distance kind of stuff per unit time kind of stuff than the light, because you can't go faster than light. But we get there as a conclusion, not as an assumption. But you could be standing still, and you'd certainly be moving pretty much just straight up, right?
Yeah.
Okay, so this is your world line.
Yeah.
All right, so now you can start assigning times to positions just by carrying a clock with you. So that's what you do. You mark these positions. You leave little stationary satellites or something. I don't know. You leave little markers so you know what time you were where. And now let's say that this happens at noon, right? So there's noon on your clock. So what you do, you think, okay, I see noon coming up. Here we are, like 4 seconds before noon. I'm going to send out a light beam. And it goes off there at 45 degrees. But now it's dusty out, or there's smoke in the valley, right?
Yeah.
So some of that light reflects back. And what you pay particular attention to is the light that is reflected back to you at 3 seconds after noon. Oops, should have been 4. I did 4 here, so let's... 4 seconds after noon, you get light reflected. Well, the dust particle out there that reflected that light, how far away is it? It's got to be 4 light seconds, right? You send it out 4 seconds before noon, it arrived back 4 seconds after noon, so it had to go out 4 light seconds and come back 4 light seconds.
Oh.
We agree on the speed of light.
Yeah.
It's got to be that. So,
Question though.
what's the time of that event? Well, it goes out 4 light seconds, it comes back 4 light seconds, so this was noon when it was reflected. In your frame of reference.
Right.
Okay? So, now you do this for a whole bunch of points, right? You send out a signal at 2 seconds. And
So all signals follow the path of light.
What's that?
All signals follow path of light.
All light signals follow the path.
Oh, light signals.
Yeah,
Okay.
Davis doesn't. Davis is going this way.
Okay.
All right, so we're going to build up a whole lot of points like this, and I'm just going to come back to something like that. And what you see is, if I connect the dots, right, that is the set of points in this two-dimensional space-time which comprise Davis's everywhere at noon. That's your x-axis. So your times you measure along your world line, and distances you set up by reflecting a bunch of light and noticing where it turned. So these are your x and t axes, and clearly I can now associate with any point. I have some time, some x and some t. So by giving an x and a t, I can locate any point in spacetime. So you've used only light to construct a coordinate system for spacetime for yourself.
So how many points do we have for one noon?
Infinite.
Infinite.
Right. So that's the x-axis. That's a continuum.
So how do we put that like the real noon? Like noon is one time.
Noon is right. Noon is time for Davis. Right. Now another observer is going to set up a different system.
No, what I mean is like
Yeah.
at a different time we had a different noon, although they are connected by one line. At another different time we had another noon.
No, it's the same noon.
These points all are at t equals 0 for Davis.
Yeah.
So which is noon?
All of them.
Yeah.
Right.
There are
This
different
is
places.
everywhere at noon. Right. A line like this is everywhere at 2 seconds after noon.
So why do we now call that the x-axis if we don't care about its extension outside, only at the point in time?
No, we do. We want the whole line.
So what do we call the individual point? Noon, x-axis? I don't know if you get my point.
No, I don't. Right. Let's
Okay.
look at x and y.
Okay, so
These are all points at y equals 0.
yes. So what are these points? X.
Different values of x at y equals 0. This is x1, y is 0. This is x2, y is 0. So we have a label for every point. This is some x3 at when y equals 0. So points along here all have some value of x and 0 for y. Points up here, if this is y equals 2, any point along here is some x and y equals 2.
So it's just a given instant, like at a given instant, it's every point.
Yeah. So at a given instant, where are things relative to Davis? Well, they're along that line.
Okay.
That's what we're after.
But my question is,
Yeah.
this exercise seems to me to be a local exercise. Like you could not.
Well, it could be 4 light years.
Because in my head, it's like it wouldn't make sense to ask, what time is it now in the Andromeda galaxy? Right? It's somewhat of a meaningless question.
Let's see. Yeah. And now, okay. So the Andromeda galaxy is,
It's about 4:50 p.m.
I see, right?
You see it at some point. Well, that there was some light travel time.
Yeah.
So if you know how far away it was, well, on your x-axis is some distance away, then now you can calculate, how what you're seeing. What you're seeing was the Andromeda galaxy as it was some time ago.
Yeah.
Right? Whatever that light travel time is, 10 million years or something.
So in which case you would still know what time it is.
You can compute it
You would say this is what.
if it's still alive.
Well,
I'm just kidding.
yeah, okay, so
if it's still alive.
Yeah, this is.
there isn't a notion of simultaneity, right, anymore, right? You can't say, oh, these two events are simultaneous. They might be simultaneous for a given observer.
And which is what you're trying to
Yeah.
construct.
So these points are simultaneous for you,
Yeah, okay.
right? Another observer, who wants to be the other observer?
I will. Yeah, I was going to say, Josh is ready.
Josh is ready. Well, Josh is always in a hurry, so he's flying faster.
There we go.
All right, so he does the same construction. He sends out light here, and let's see. This is, you two cross paths here. Wave, keep going. So he's marking off times here, and mark a few of these, and when it comes back, it's let's see. It's supposed to be a right angle. Something here. And okay, so we do other curves like that, and what we find is that Josh's the set of points simultaneous with Josh's noon lie along a line like this. You notice how they've kind of scissored?
Mm-hmm.
Well, what they have scissored around is light. This is the way that both of you, for light, measure the same delta x over delta t, right? By these things scissoring this way, that's how you can graphically represent two observers traveling at different velocities, but still measuring the same value for the speed of that green line. Okay, this is how it works. Now, this is not Euclidean space. You cannot look at this diagram and just measure distances with a ruler.
So is that
it
light?
doesn't work that way.
Is that light traveling in the same direction of our initial light?
Well, it was supposed to be a straight line.
Yeah, sure.
Yeah, light always moves. Yeah, that's moving to the right.
It's going to be the
It's moving
same.
to the right, and both of them observe this moving to the right. Right, that light is still moving to the right, and for put the green right here. So for Josh, okay, so let's see, we construct something like this, and those two are equal, and he says, oh, speed of light. And Davis does the same thing, comes out here and says, okay, here, and speed of light. So, an equal distance along Davis's axis in an equal time. 1 light year in 1 second, or 1 light year in 1 year here, one light year in 1 year here. But those light years aren't the same. Those years aren't the same. But the speed of light is.
Basically, it all comes down to is you need your speed of light to be some invariant.
Yeah.
Well, the speed of light is invariant. That's one of the fundamental postulates of special relativity.
It's now even
So-
a definition.
Yeah, it's
Yeah, but
Yeah,
then
it's-
that's
it's definitional. I mean,
that's an
Newton didn't need the speed of light to be constant,
Yeah.
right? Einstein, yeah.
But does this start to break down if I suddenly hit, a wall of water and now my speed of light has changed?
No, because the postulate states the speed of light in vacuum.
Yeah.
Right? Yeah, it goes. Light goes slower than the speed of light in water.
Yeah.
Right. That's why you get Cherenkov radiation.
Yeah.
Right. Yeah. Fine. Cool.
Yeah.
Blue. Eerie. Neat
Yeah.
stuff. Right.
Yeah.
But no, we're talking about the speed of light in vacuum. Right? And yeah, it can be anything else in a medium because light interacts with charges.
Yeah.
Right. So if it's passing through something with free charges, its speed is going to be something different. It's actually,
It's going to slow down. Want to say hi to the charges
Yeah.
and spend some time with them, hang out with the charges a little bit, what's up? No,
Yeah.
slow down.
Okay. So,
Yeah.
what we do demand of space-time, this seems new to y'all, so I'm just going to keep going. I don't hear any cows.
No.
Okay.
Yeah. Smart aleck. Okay. We would like space-time to be a vector space. I mean, after all, over here, what are we doing? We're locating events. So, Davis says, I'm interested in what's going on at that position in that time. That's called an event. And I locate it with a vector. So, what we want are...
Oh, do these guys have a class in here?
Oh, I don't know.
You guys waiting for the room?
Yeah, there's a recitation. We got it at 5 though. Yeah.
At 5?
Oh, it's almost 5 already.
Okay, thanks.
There's the
All
cows.
right, all right.
The cows showed up.
We'll talk about this
All
a
right,
bit more.
on Monday.
But the key thing about a Lorentz transformation is, it's going to relate Josh's and Davis's frames of reference, but it's got to be a linear transformation to preserve the vector properties.
After 100 years,
Yeah.
it's still confusing. Time and space.
Oh yeah.
Like in this format,
If you work with it, it gets sort of okay.
I like to think of it from a concept and then make the math match the concept. Otherwise, I don't get it.
See, from